Hello everyone and welcome to another video. So this week we are on to week 9 in our AE501 journey. So we're at the second to last week of the quarter. So let's just jump right into it and talk about where we're going this week. So for week 9, we're shifting gears. So remember last week we finished up our discussion on partial differential equations, and now what I'd like to do in week 9 is I don't know if I want to say this, but this is the part of the class that I want to go the most quickly through, namely that is the probability discussion. So you're going to see that these first 4 videos and modules are looking at various different types of analysis related to probability. So we're going to look at some basic probability to get started, and then I want to look at a couple of different ideas, like namely how to look at probability distribution functions and cumulative distribution functions. And then we're going to look at 2 separate distributions that are very important. One is the binomial distribution, and then this Gaussian/normal distribution. While this is probably the most popular type of probability distribution function, I'm sure you've heard of a bell curve or a Gaussian or a normal distribution. These are all the same things. This is an important discussion, but there's just too much interesting stuff in this class, so what I decided is we're going to make this video optional. There's no required homework that requires this discussion, but I did want to put it up here because, like I said, it's very popular. You're going to run into it all over the place in engineering and science, so I wanted to give some background on that, but I am more excited about some of this other material. So I've decided to trade some of the content. So namely, you can watch the Gaussian and look at this stuff if you're interested. But I think what's more important is the optimization. So that's the other part that I want to talk about here in week 9. You're going to notice that I'm actually preloading some of the week 10 material here. So week 9's discussion on probability is actually a little bit thin. There's not a ton of required viewing here, but instead, like I said, I really want to start talking about optimization because I think that is actually the most exciting part of this class. So I want to give it an appropriate amount of coverage and time. So that's the game plan this week. Is we're going to look at probability here. So week 9 is technically like a probability week, but we are going to prime the pump, so to speak, and get our discussion ready for optimization coming down the pike next week. So the videos that are required for this week are 3 probability videos and 2 optimization videos. Okay, so with that being said though, let's go look at the homework and see how this is reflected. Alright, so here's homework 9. And what I'll say about homework 9 is, A, it's all focused on probability, and B, it's not very long. Now, I know there's a lot of words on this page, and you might look at problem 1 and be like, oh my gosh, there's part A, B, C, D, E, F, but really, this one is not that complicated. It's looking at an idea of using Venn diagrams to represent probability, and in fact, we talk about this pretty extensively in this video here, where we talk about basic probability. This focuses on this law of total probability, and in fact, you can actually see, let me see, I think I even go through an example, yeah, here kind of near the end of the video, which is very, very closely related to the homework problem. So what I will mention again is, I know I've been harping on this all quarter, but watch the video first with after you've read through the homework, just so you understand what's expected. And I think once you see what's expected and you watch this video, you'll say, oh, hey, this is pretty much very applicable to the homework. I'll just pay attention here, and I think you'll be on your way. So like I said, I don't want to spend too much time talking about problem 1 because I think it's pretty self-explanatory once you watch the video. You're really just drawing a bunch of Venn diagrams and overlapping probabilities and calculating various probabilities about different events. So that's what problem 1 is. Okay, problem 2 and 3 and 4, actually, you're going to notice have this big optional flag on it. So like we talked about at the beginning of the quarter, these optional problems are, again, they're things that I've had from the past. I wanted to keep them because I think they're interesting, but given the fact that we want to focus on more interesting things in this class, I'm not going to make these required. And in fact, that's why they're optional. And again, there's no extra credit available. There's no penalty for not doing these. So if you want to play with these, feel free. I'm happy to answer questions, but the TA is not going to look at these for any grading at all. So they are completely 100% optional. So again, let's not talk about them too much here because, like I said, I can't imagine too many people are going to spend a ton of time on this. So problems 2, 3, and 4 are optional. Now, that being said, I do want to spend a little bit of time talking about problem 5. So problem 5 is not optional, and I think it's kind of fun because we're going to be simulating some interesting events. So problem 5 is looking at simulating a binomial distribution and seeing how this might apply to things like games of chance or things like that. So the first thing I want to mention here is I have a function called roulette wheel. It's a MATLAB function that I wrote that basically is used to help simulate spinning a roulette wheel. I think everyone knows what the game roulette is. Now, the only thing that's interesting about this is my function is going to allow you to simulate a unfair roulette wheel, right? Roulette is pretty fairly fair, right, in the sense that all the slots are the same, so you have an equal probability of landing in any of these slots, but my function is actually going to allow you to simulate kind of interesting off-nominal scenarios. And the way you get to this roulette wheel function, again, I should probably mention this, is as you're watching the video on the binomial distribution, okay, this again is one of our required videos for this week. So just like every week, you can basically come here and get lecture notes and code associated with the video at my GitHub page here. But I also am going to include a separate link here in the description of the video to my other GitLab page where I have all of my MATLAB code that is available for your consumption and actually public consumption for that matter. So if you come to this second link, this takes you to the GitHub page where you see I have an entire MATLAB software development kit. I've got some various functions that are helpful for probability. The one that you probably care for this homework is just this roulette wheel function. So I've got documentation here. I'll let you read this, and basically what this allows you to do, like I said, is simulate spinning an unfair or slightly biased roulette wheel, and you can pick how biased you want this thing to be. So again, I'll let you read this documentation. Hopefully it's somewhat self-explanatory. Email me if you have questions, or I'm happy to talk about this during office hours. Okay, so that gets you this roulette wheel function, and what I'd like you to do now is just go ahead and test to make sure you know how to call that function, and you can use it to simulate different things. Like, for example, can I use this function to simulate throwing a completely fair six-sided die, right? And then, can you use that function to simulate a situation where you have a biased or kind of a cheating die, right? Where the numbers 3 and 5, they occur with way higher probability than the rest of the other values, okay? And then also the third case here is maybe spinning a roulette wheel, which instead of having, I don't know how many actual slots a roulette wheel has, but I want this roulette wheel here in case I to only have 4 slots. And these slots are, again, not even. You can see here that landing in slot number 3 is way more likely than landing in these other slots. Slot 2 is, you know, pretty high probability as well, but slots 1 and slot 4 only have a 10% probability respectively, okay? So at this point, you've got this roulette wheel function. You can simulate all these kind of interesting scenarios. Now what I'd like to look at is, let's make up some game where this game is really kind of silly. All you're going to do is you have a single die, right? This die has 6 different sides on it. Okay, and all you're going to do is you're going to roll this thing 5 times in a row, okay? And you're going to make up a hand comprised of what numbers show up on these 5 rolls. So, for example, you could roll a 3, and then a 4, and then a 3, and then a 3, and then a 5, okay? And the way this game works is all you're going to do is count how many of the same numbers did you get. So in this case, you got a 3, 3, 3. So there's 3 3s. And this would be like a hand of value 3, because that's the number of matches that you have in this hand. Now, I don't care about the actual numerical number of the match. I just care about how many match. So what I mean by that is, if you also rolled a 5, 5, 1, 3, 5, you can see in this case, there's a 5, 5, and a 5. So there are 3 instances of 5s. So this is also a hand of value 3. It's got 3 matches. So this hand would tie this hand exactly. Nobody wins, nobody loses. It's an exact tie because both of them have 3 matching numbers, okay? So now what I'd like to consider is, let's say you're playing this game with some opponent. The opponent rolls this hand, okay? I want to know what's the probability that you are going to be able to beat his hand if you decide to play this game completely fair and you use a die where each side has a 1/6 probability of showing up, okay? So that's what part C is. Just, can you calculate that probability? Now, part D is where this gets interesting. I'd like you to go to YouTube and just enter this into the search in YouTube. So there's a movie called Rounders. It's all about gambling. There's this scene where the the two protagonists go into a card game with a bunch of sheriffs, and they are going to try to cheat to win some money. What I'd like to do is kind of simulate that and see how likely are we to win if we decide to cheat, and are there any potential negative drawbacks of cheating. So what we're looking to do here is, let's go back to this situation where here's what your opponent dealt, right? Now, let's put put ourselves in the shoes of a cheater, and let's say I've got 3 die in my pocket that I can choose to use to try to play against my opponent here. So 1 die, here, number 1, it has these probabilities on each of the faces. So you can see here that the number 5 is a little bit more likely than any of the other numbers to show up. So you could actually potentially probably have a better likelihood of winning using this die number 1, right? Because you're more likely to get matches of the number 5, okay? So this die, let's call it a low level of cheating. Then let's say you've got a medium level of cheating die here. This one, you can see the number 2 has, you know, a significantly more higher chance of turning up than any of the other faces. So this die number 2 has a medium level of cheating, but it's going to get you a higher probability of winning, right? And then finally, you have this like mega cheating die where it's super biased, right? The number 6 is going to come up half of the time. So you are very likely to win if you decide to pull out this number 3, okay? And use this to play against your opponent, okay? So what I like to do here in this part, D, is what's the probability that you're going to win if you go ahead and use die 1, number 2, or number 3. So this is to get you an idea of what are the probabilities of winning, or the likelihood of winning, depending on what level of cheating that you would like to engage in, okay? So you can analytically calculate this using the binomial distribution, but what I'd like you to also do is create a MATLAB simulation that basically plays this game, right? It rolls a biased die using the roulette wheel function that we looked at earlier, and you play this like 10,000 times and just see if numerical simulation validates your analytical answer here, okay? So that's what part D is about. Part D is kind of fun. It's comparing some numerical simulation with analytical results. Okay, now let's get back to this idea of the possible consequences of cheating, okay? So you can probably guess that if you use this die, this has a low level of cheating, so it's actually probably pretty likely that you're going to get away with it, right? There's a low likelihood or low probability that you're going to get caught if you use a die that is only a little bit biased, right? But if you use a die that's a little more biased, your probability of getting caught goes up, you know, somewhat significantly. And then if you decide to really cheat with this totally loaded, weighted die, there's a very high likelihood that you are going to get caught cheating, okay? So let's say that you are playing your opponent, and if you get caught, what's going to happen is your opponent is going to fight you and beat you up, and it's going to send you to the hospital, and it's going to cost you $3,500 at the hospital, right? Now, what if there was $4,000 on the line? Do you cheat or do you not, given this scenario? So given the scenario that your opponent rolled this, you have these different die that you could potentially use, you have this probability of getting caught, it's going to cost you this much if you're caught, but you're going to win this much if you get away with it, okay? I would like you to make a decision and do some engineering analysis and decide which of these biased die would be a good idea to use, okay? So, what we're going to assume here is, again, I'll let you read this, but assume that if you get caught cheating, you're not going to win, right? They're not going to give you the $4,000 even if you happen to win. You're just going to the hospital and you're going to have to pay $3,500, right? But if you get away with it and you're able to win, you get this much. You get $4,000, okay? And what I'd like you to do here is consider the case of, let's say you're not very smart and you're presented with this same scenario every single weekend that you go out. So 52, 54 times a year, right? You go out and every single time there's $4,000 on the line, there's $3,500 that you might have to pay if you go to the hospital, and you got to make this decision again. In other words, pretend you're presented with this exact same scenario many, 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 many different times, and I would like you to decide, what should you do each of these times. Okay, and I think I'll leave it at that. That's probably a good way to discuss this. Okay, so yeah, like I said, that is what we're doing for week 9. What I will recommend is, because you can see this homework assignment is shorter, the oops, sorry, I'm trying to bring this document up. The video assignments on the probability section are shorter. Make sure that you do get a head start on this optimization, because, like I said, just peeking ahead for week 10, we'll talk about this later, but there's a pretty full schedule next week in terms of both the lecture material as well as a pretty fun but beefy homework assignment to close out the quarter. So like I said, don't rest on your laurels here in week 9. If you get a little bit of extra time and you find yourself finishing homework 9 a little bit earlier, I would recommend getting a little bit ahead in the lecture discussion. And in fact, I'll also make sure that homework 10 is posted in case people want to take a peek at that and get chomping on that now. So, okay, I think that's probably it for this week. I think let's leave it here, and hope to see people in office hours. Okay, thanks everyone. Bye.